Hey everybody, this is going to be a quick video on how to find asymptotes of a rational function. So when I say asymptotes, there are different types of asymptotes. There are vertical asymptotes, which finding vertical asymptotes of a rational function, it's pretty much the same no matter what the rational function is. There are also horizontal asymptotes that might occur with a rational function, and the strategy for finding a horizontal asymptote is slightly different depending on the function. There's also a third kind of asymptote that comes up now and then, which is called the slant asymptote. So we're going to look at how to find any of those asymptotes. Okay, so first of all, just to kind of clear things up, a rational function, by the way, is any function that can be written as p of x over q of x, where both p of x and q of x are polynomials. So just kind of putting that out there. So an example of a rational function might be something like 2x squared plus 9 over 5x squared minus 7. So first we'll start with vertical asymptotes. Here's our rational. This is an example of a rational function. So for vertical asymptotes, that all is going to depend on the denominator. In particular, vertical asymptotes are going to occur at what I like to call the problem points of the rational function. What does that mean, problem points of a rational function? Well, all rational functions need to be, you kind of need to be aware of the whole dividing by zero issue. Meaning there might be certain values of x that we could plug into this function that would result in the denominator being 0. And whenever that happens, in particular in a rational function that has been factored and simplified, if there are values that would make the denominator 0, those are going to be asymptotes. Again, assuming that it's a fully factored, fully simplified rational function, which this one is. We can't simplify that at all. So where are the vertical asymptotes? Well, we can find that by just solving where does the denominator equal 0. That's really all that it's going to come out to. So we're going to solve 5x squared minus 7. Where does that equal 0? Well, solving this thing out, add 7 to both sides and divide by 5, we get x squared is 7/5. Taking the square root, and remember the square root property, x equals plus or minus the square root of 7/5, which this is technically the answer. This is where the vertical asymptotes are at. Very frequently in college algebra, you would be asked to rationalize your answers. Rationalizing means like if you have something where there's a square root in the denominator, you want to rewrite it in a way so that there's not a square root in the denominator. And here we do have that, because when you're taking the square root of a fraction, you can really break it up into the root of the top divided by the root of the bottom. So this is the same as the square root of 7 divided by the square root of 5, plus or minus root 7 over root 5. And I want to rationalize that because I have that root in the denominator. How do I rationalize it? Well, at least with square roots, it pretty much just amounts to multiplying top and bottom by the root. So root 5 by root 5 over root 5. You just multiply through. Root 7 times root 5 is square root of 35. You just kind of multiply them under the hood. Square root of 5 times square root of 5 becomes 5. So these are the vertical asymptotes right here. Would be at x equals plus or minus square root of 35 over 5. Those are the vertical asymptotes of this rational function. And for rational functions, this is always going to be the case, assuming that you have rationalized, or you've simplified. So let me just really quickly, I don't want to make like a big deal out of this, but an example of what I mean by simplifying is, suppose that you have some rational function, you go through, you factor the top becomes x plus 1 times x plus 2, and the denominator is x plus 2. Well, and I'm going to put this in quotes, this is kind of equal to, if we cancel out the x plus 2's, this ends up looking a lot like x plus 1. But we still can't plug in x equals -2 because the actual function is given by this. This is the original function, and we cannot plug -2 into that. So this ends up being something called a removable discontinuity. And just a quick graph, so this ends up looking a lot like x plus 1, so it'll look something like this, but then right here at -2 there would be a hole. So that's what this graph will end up looking like. And the only reason that I mention this is because I was saying with the vertical asymptotes, all that you have to do is solve for where the denominator equals 0. But that's only once you've kind of canceled and reduced and simplified. So this doesn't have an asymptote at -2. When something cancels out of the denominator like that, it's going to always be a removable discontinuity. But if you have a rational function where it's been factored, simplified, anything that cancels out, that's when you can just set the denominator equal to 0, solve it, and that will give you the vertical asymptotes. Okay? So now let's talk about the horizontal asymptotes. And with horizontal asymptotes, it really kind of has to do with, like the way to logic through it is let x go to positive infinity, see what happens there. Let x go to negative infinity, see what happens there. And that's how you can find if there are asymptotes. If at positive and negative infinity the function is approaching some value, those are going to be the horizontal asymptotes. But we can also break it down just into like some cases or some rules, in particular depending on the degree of the numerator and the denominator. The degree, by the way, if you remember, the degree of a polynomial is the highest exponent that is attached to an x term. So with this example right here, the degree of this top, the degree of the numerator is 2. The degree of the denominator is also 2. So it's whatever like the largest exponent that is attached to x. That's the degree of the polynomial. And comparing the degrees of the numerator and the denominator allows us to determine exactly what kind of horizontal asymptote we have. So case 1, if the degree of the numerator is less than the degree of the denominator, then there will be a horizontal asymptote at y equals 0. So an example of this might be something like x over x squared plus 9. This has a horizontal asymptote at y equals 0, which is the x-axis, y equals 0. So as long as the degree of the numerator is less than the degree of the denominator, so here the degree of the numerator is 1, the degree of the denominator is 2, means there's a horizontal asymptote at y equals 0. Second case is if the degree of the numerator, and I'm going to shorten it here, is equal to the degree of the denominator, then there's a horizontal asymptote at and this might sound a little strange, it'll be really obvious when we look at an example, at the ratio of leading coefficients. So the leading coefficient of a polynomial is the coefficient that is attached to the highest degree term. So let's see, what's an example where we might come across this? Oh, right, the one that we were looking at earlier. So an example of this is 2x squared plus 9 over 5x squared minus 7. The degree of the numerator and the denominator are equal. The leading coefficients are 2 and 5. There's a horizontal asymptote at y equals 2/5. So it's literally just take the leading coefficients, assuming that the degree of the numerator and the denominator are equal, take those leading coefficients, that ratio, that's where the horizontal asymptote will be. So in this case, there's a horizontal asymptote at y equals 2/5. The final case, I think that you see where this is going. This is where the degree of the numerator is greater than the degree of the denominator. And when this happens, there's not a horizontal asymptote, there's something that we call a slant asymptote. which is neither horizontal or vertical. It's just like a straight, a linear line. That's, you know, a diagonal. You might also hear it called a diagonal asymptote. It might be strange to hear it called that, but yeah, that would fit. And so how do we find that? Well, we find that through polynomial division. So it's found as the quotient of polynomial division. So let's look at an example. Let's see, here's the back of, did I use the back of this? Here, I need another page. Right, sorry, I'm just rearranging here. See if I can keep all of this kind of still on here. All right, so for this last scenario where the degree of the numerator is greater than the degree of the denominator, here's an example where that comes about. 3x squared minus 2x plus 1 over x minus 1. We want to figure out what is the asymptote for this thing. What is this? It's going to be a slant asymptote. So what we do is we just do the polynomial division, and whatever the quotient is, the result of that polynomial division, the quotient is the slant asymptote. So with this one in particular, we can do synthetic division, so I will do that since it's faster, just to try to not make this a long video. I'm trying so hard to make these shorter videos. It's tough. I have a synthetic division video. Go check that out if you don't know how to do synthetic division. So here I've got everything all set up. Bring down the 3. 1 times 3 is 3. Negative 2 plus 3 is 1. 1 times 1 is 1. And then these things just, yeah, they just cancel out, right? Yeah. Oh, no, sorry. It becomes 2 because we're adding. And this was an x squared term. This is x, which means that the quotient is 3x, or the result of this whole thing is really 3x plus 1 plus 2 over x minus 1. But the quotient is the slant asymptote. So the slant asymptote of this thing, I'll abbreviate it dA, diagonal asymptote, is given by y equals 3x plus 1. Okay, that's the slant asymptote. So the things that you'll run into, the things that we looked at in here, is how to find vertical asymptotes, what happens when you kind of cancel a denominator out, that results in a removable discontinuity, how to find horizontal asymptotes. Whatever questions you got, throw them my way.